So they want a Taylor series for the following function centered at this a value. So we know what the Taylor series looks like. Where it is convenient that a is 0. So we have 0 here and 0 there. And we understand that fn represents the nth derivative of this original function. Maybe we can make a list of the first, let's say, 4 values of n. Now let us compute some of these derivatives, where the 0th derivative would be the original function. And now we compute the first, second, and third derivatives. We can go quickly through that. So now we would like to evaluate each of these iterations at a equals 0, because that's what this tells us to do. This tells us to compute the nth derivative and to then immediately plug in a, but a is 0. So let's plug 0 in for here and here and here and there. So now we have these numbers which play the role of coefficients to this term, where we have a factorial denominator. So let's build the first few terms. So with n equals 0, we would have -1 over n factorial, but n is 0, times x to the power of 0. Because remember, a is 0, and for this step, n is 0 right there. So let's do this all over again, but now pretend that n equals 1. So -3 is this coefficient here, this numerator. We would get back this here. And now let's do the same thing for n equals 2 and n equals 3. Understand that this process goes on indefinitely. Now let us simplify and reduce some of these terms. So if the instructor is content with this, this is the answer, because this is the Taylor series for this function at this point. Of course, this is just the first handful of terms. This is what we mean by ... It goes on forever. However, if they want you to take these terms and to repackage them back into sigma notation, we can do that. So maybe first we can factor out a negative. And now we look for patterns inside so that we can build a series or a summation. So we keep the negative outside. And now we need an expression here that can generate these specific terms. Well, the simple part is the x, because this would of course just be x to the power of n, because this here, it's x to the power of 0, x to the power of 1, x to the power of 2, and so on. However, these coefficients are kind of tricky. 1, 3, 6, 10. That's a tricky sequence, because it's not obvious how we're going from 1 to 3 to 6 to 10. Yes, I see that from here to here you go up 2, and then here to here you go up 3. Here to here you go up 4, and so on and so forth. That actually happens to be a quadratic. So a quick timeout. 1, 3, 6, 10, and so on. That can actually be generated by this expression. So this quadratic expression generates these specific terms. How do we know this? Honestly, this is just one of those things that you have to see at some point, sometime, and then just realize that it exists. Okay? So let's take this here and just drop it in right there or beside it here. It doesn't really matter. And this result would constitute your Taylor series, assuming that they were not okay if you had stopped here. So this is the same as this is the same as that.